Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, everybody. It's my pleasure to welcome Peter Bodick to give us a talk today. Peter is a PhD student at UC Berkeley, where he's been working on the RadLab project. He's going to tell us today about his work there on automating data center operations using machine learning. Thanks very much.
Thank you. Hi, so I'm Peter from RadLab at UC Berkeley, and I'll talk about using machine learning to operate data centers. So when the RadLab project was started about 5 years ago, the goal was to build tools that would let a single person deploy and operate large-scale web applications. And the main bet was that we can use machine learning to help us get there. And I spent 5 years applying machine learning to these problems, and today I'll talk about some of the best results we got. So before I get into the details, let me start by talking about why it's difficult to operate these large-scale web applications. The main reason is that they are really complex and very few people actually understand how they work and so on. In particular, some of the popular web apps like Amazon, Hotmail, and Facebook, they can serve tens of millions or hundreds of millions of users. They run in hundreds of data centers or tens of data centers, and each data center could have tens of thousands of servers, could run hundreds of services. This picture shows what Amazon looked like about 4 years ago. This is from our paper from 2006. And each dot on this graph shows a single service that they're running, like recommendation service, shopping cart, and so on. There was 100 of them back in the day, and now I think it's up to 200. The arrows show dependencies between services, and what happened when you click on Amazon's website, that request gets translated into often 50 or more requests to all these individual services, and the responses get merged together to form a single HTML page that gets sent back to the user. So there's a lot of dependencies and a lot of complex interactions in these systems. Here you have, again, a schematic visualization of a data center with many applications. And the really complex part is that you might have different applications and different requests for these applications that would share the same service, they would share the same physical machine, they would share the network or the databases, and understanding these interactions is really difficult. Next, the software that's running in these data centers is constantly changing. eBay published these statistics that they say they add 300 features per quarter, and they add hundreds of thousands of new lines of code every 2 weeks to their system. And finally, the hardware running in these data centers is constantly failing. Google says that on their 2,000-node cluster, which is their unit of deployment, during the first year, they see 20 rack failures, 1,000 machine failures, and thousands of disk failures. And there's many other types of failures that are rare, but more significant. So in this environment, it's really complex and difficult to operate these applications. So what are the three main challenges of data center operations? And these are the three main challenges I'll be talking about in this talk. The first one is quickly detecting and identifying performance crises caused by the various failures that happen in a data center. These crises could affect the uptime of the application, can reduce the performance of these applications, and that's why the operators have to quickly respond and fix them. And for example, at Amazon, operators often have to wake up in the middle of the night on the weekends, and they would have 15 minutes to start working on a particular problem and do it quickly. So this is really annoying for them. The second main challenge is understanding the workloads of these applications. There are both daily patterns in workload that are crucial for provisioning correctly these applications, but there are also these unexpected spikes or surges in workloads, like the one that happened after Michael Jackson died, where 13% of all the Wikipedia traffic was directed to the single article about Michael Jackson, right? So handling these workload spikes is crucial, and we would like to stress test our applications before we deploy them to production to make sure that we can handle them. And finally, we would like to also understand performance of these systems in different configurations. The problem right now is that most of the data centers are very static in terms of deployment of resources. And the reason is that the operators don't understand what would happen if we add more servers, remove a few servers, or use different kinds of servers. And it's very difficult to efficiently utilize these data center resources. So these are the three main things that I'll talk about today. So why machine learning, right? You might ask. And so as I mentioned, the data center operations are manual, slow, and static, and mainly because the systems are very complex. Having models of workload and the performance of these systems would be really useful for addressing these three challenges. But using, for example, analytical models like queuing networks is not very practical because designing these models is manual, and because these systems change too frequently, we would have to update these models manually very often. Fortunately, there's a lot of monitoring data being routinely collected in the data centers that could provide insights into workload performance and different failures. But there's so much data that analyzing it manually is impractical. These operators are not trained to do this, and doing it manually would be too slow. So that's where machine learning would help a lot, where we could use various methods and techniques that allow us to analyze large quantities of data accurately, and also combine these machine learning methods with non-machine learning techniques like control theory or optimization to create even more powerful tools. And I'll show you examples of that later in the talk. All right. So the main contribution of my work is using machine learning techniques to take the data center monitoring data and build accurate models of workload, performance, and failures in these systems, and use them to address the three challenges I described at the beginning. I worked on four main projects, and let me just quickly go over them and highlight what were the different challenges and what modeling we used in each of them. So in the first project, the goal was to detect performance problems or different failures in a web application that might be hard to detect automatically or by operators. The input was the workload trace or the behavior of the users on the website. We used anomaly detection techniques to spot unexpected behavior of the users, and these would often point to performance problems or on failures in these web applications. The second project was on identifying these problems. So the input was were all the performance metrics being collected on all the servers running an application. We use feature selection techniques to pick a smaller set of these performance metrics and then create a crisis fingerprint that would uniquely identify a particular performance problem so that we can then later automatically recognize whether a particular problem is happening again and again, and the operator doesn't have to do this manually. The third project was on modeling workload spikes. The goal was to create a workload generator that we could use for stress testing web applications. So we created a generative model with a few parameters that lets us synthesize new workload spikes, and we use that internally to run various experiments. And finally, the last project was on performance modeling. We designed both kind of black box models of these web applications, but also we combined the structure of these systems or structure of these queries that you run inside these applications to provide accurate predictions of latency that extrapolate to new workloads and new configurations so that you can use them to answer various what-if questions as if you're the developer or the operator. We also combine these performance models with control theory to do dynamic resource allocations in both stateless systems like web servers or a storage system when you actually have to copy data over to the new machines. So, yeah.
Were these all based on actual traces from companies like Microsoft, Amazon?
You mean all these projects?
So
so let's see. So the first one, this one was based on data from eBates.com. So this was an actual company that gave us traces from for some of their failures that happened. This one was in collaboration with Microsoft during my internship. The spike modeling, we had some traces that are publicly available, and I'll go into that in more detail later. And all the performance modeling was done internally on applications that we had available, using benchmarks and workload generators that we had available. So these were not real systems or production systems, I should say. Yeah. So in the rest of the talk, I'll talk about the crisis identification project and a characterization and synthesis of workload spikes, and then I'll summarize. So the crisis identification project is the project I worked on during my internship at Microsoft Research Silicon Valley with Moises Goldschmidt. The main use of machine learning here was taking all the performance metric being collected in a data center for one particular application, and using feature selection methods to select the small relevant set of these metrics to create an accurate crisis fingerprint that you can use to uniquely identify these various performance problems. So as I mentioned, there's a lot of failures happening in data centers. Could be hardware failures, but could also be software bugs, misconfigurations, and so on that cause either downtime or reduced performance of these applications. And these cost a lot of money, and that's why there are operators who have to really quickly respond when they happen. So here let me first show you what happens during a typical crisis in a data center. On the left side, you see a timeline where the application was okay, and then at 3 in the morning, there's a crisis that's first detected, right? The detection part is the easy part. It's usually automatic, and you detect it by violations of performance SLOs, right? For example, you notice that the latency is too high or the throughput is too low, so that's relatively easy. When the operator wakes up, opens his laptop, he has to perform crisis identification. So he starts looking at performance metrics, logs, logging into machines, and so on to identify what the problem is. He doesn't have to do root cause diagnosis necessarily here, just needs to understand enough about the problem to fix it. Maybe rebooting a machine would do it, and so on. And this part, the identification part, could take minutes or maybe hours sometimes, and it's really manual and difficult. After they figure out what's going on, they perform resolution steps, which depend on the type of the crisis. And once the crisis is over, that's when they perform root cause diagnosis and add the description of the crisis into a trouble ticket database.
Do you also consider crisis like attacks, external attacks on security?
No, we were not considering that. We were mostly interested in performance problems, but and we were interested in problems where you can fix them by maybe rebooting machines, restarting processes, and so on. So in that case, but some of the techniques might apply, and you can ask later to see if some of that would apply. So our approach of fingerprinting was we evaluated on data from exchange-hosted services, which on data from about 400 machines, where every machine was collecting about 100 different performance metrics. To give you an idea of how we actually want to help the operators, imagine that you have a system where you already observed 4 different performance problems. Right there, the application configuration error may be repeated twice. And so what operators already have is this trouble ticket database. Right? For every type of a problem, they have a description of the problem, how they detected it, and resolution steps that they take to resolve this problem. What we're going to add is a fingerprint. For every type of a problem, we'll add a vector describing that problem that we can automatically compare. And when a new problem happens, what we'd like to answer is this crisis that's happening right now a crisis we've seen before? And if it is, we'd like to know which one it is. And if it's not, we'd like to tell the operator that this is a new type of a problem. And even in that case, this helps the operator because he doesn't have to manually go over all the past problems and try to find the one that's similar. And so what we do is we create a fingerprint of the current problem and we compare it to all the past fingerprints in our database. And if we find one that matches, this is our answer, and this is what we tell the operator. So this is the overview of our technique. There are two main insights here that lead to our solution. The first one is that these performance crises actually repeat often. There are various reasons for this. For example, the root cause diagnosis could be incorrect, so the developers actually fix the wrong problem, and the crisis keeps happening again. Or just deploying the fix to production might take time because of testing, and might be weeks before it's actually deployed, again causing the crisis to reoccur. And we've seen this both in the EHS data and also in Amazon's. During my internship at Amazon, it was some of the less severe crises happened really frequently. And they were not significant enough that the developers would fix them quickly, but the operators still would have to wake up in the middle of the night to deal with them.
Do you have a sense of what fraction makes you wake up in the middle of the night? I mean, how many are recurrent and how many are new?
You'll see some statistics later for the EHS. For Amazon, the way they classified the crises were they called them SEV1 and SEV2 in terms of severity. The SEV1s were the ones that where you absolutely have to deal with it right now because you're losing money right now. The SEV2s were about 100 times more frequent. It depends on what service you're talking about, right? But this particular application that we looked at, they were about 100 times more frequent. They're not ones that directly are affecting performance right now, but if you don't deal with, fix that problem within an hour maybe, they could lead to a lot more serious problems down the road.
How many were recurrent? In other words, how many?
I don't have statistics, exact numbers on that, but for the EHS data, we had about 19 labeled problems, and out of that, there is one crisis type that repeated 10 times. And there was one that repeated twice, and the other ones just happened once in the data set that we had. Okay. The second insight is that the state of the system in terms of performance metrics that you're collecting is similar during identical performance problems. Right? If the same thing happens twice, the performance metrics will not be exactly the same, but if CPU might go up, and network traffic might drop, and so on. And this is exactly what the operators use when they are personally trying to identify these problems. But capturing this system state with a few metrics is difficult because for different problems, you need different metrics. And often, ahead of time, you don't know which are the right metrics. For example, the operators from EHS gave us 3 latency metrics, which they said were the most important metrics for that application. This is what defines actually the performance SLO for this application. And when we tried to use just these 3 metrics for creating the fingerprints, there was not enough information to actually identify the problem. So you need to look into a lot more other metrics of the system.
When you say system state, do you necessarily mean unobservable system state, or it's just the thing that you are not measuring against?
So I don't mean application state like user cookies and so on. I mean just the performance metrics that the operators would use to identify the problems. And so these would be CPU utilization, workloads, latencies, throughputs, queue lengths, some things that metrics that you can measure in your system.
So system state and metrics are actually.
That's what I mean by that. Yes. Yeah. So in this particular case, we used the system state were exactly performance metrics, but you could add other metrics into it that are based on logs and other things that that might be useful for crisis identification. Right. There are 3 contributions in this project. The first one is the creation of the fingerprint. Fingerprint is a compact representation of this state. The main goal of this representation is that it should uniquely identify a performance problem. It should be robust to noise because even though the same crisis happens twice, the performance metrics will not be exactly the same. So we'd like to make sure that the fingerprint is still similar. And finally, we also wanted to have an intuitive visualization of the fingerprint. So when the operators use these fingerprints, we'd like them to understand what's captured in there, even if they don't understand the exact process of how we created this fingerprint. The second contribution is the real-time process of how you use these fingerprints for crisis identification. As I explained before, the goal is to maybe send an email to the operator that's when he wakes up and opens his laptop that says, the crisis that you're looking at right now is very similar to the one we saw 2 weeks ago, and here is the set of steps you need to take to fix it. Or we could also say, this is a problem that we haven't seen before, and you should start debugging yourself and start looking into the details of the problem. And finally, we also did a rigorous evaluation on data from EHS.
How long was that data for? You said 400 servers, but for
we had 4 months of data, and so that was the main data set we used. These are the majority of the main problems they had. There were some that I think we didn't use because they couldn't give us a label for it. But I think these are definitely the vast majority of things the big problems that happened during the 4-month period.
Do you have a sense of, were there anything that went undetected?
There were things that we saw in the data in terms of high latencies where we talked to the operators and they didn't have any record for that. So they didn't see any emails going on that describing this problem, even though we clearly saw that the latency was up. And there were a few instances of that. So those were the ones where we thought something happened, but they didn't either didn't know or there were no emails at least, so they couldn't give us a label for that problem. Yeah.
Do you only use snapshot of the system state as features, or does that also include some accumulated stats?
So the data we use were aggregated into 15-minute periods. So they were, like if it might have been an average CPU utilization during a 15-minute window. And the reason we use it's 15 minutes and not say 1 minute is that this was data from some of their historic databases, metric databases. So I think in real time they are collecting the data in much finer granularity. It's just the data we got from them were over a year old in some cases, so they didn't have all the detailed statistics in this case. Okay, so in the rest of this section, I'll talk about how we define these performance crises, define the fingerprint, and go over the evaluation. The definition of a crisis in general is that it's a violation of service level objective. It's usually a business level metric, such as latency of the request happening on the whole cluster. An example of SLO that we used or that the EHS used is that at least 90% of the servers need to have latency below 100 milliseconds during this 15-minute epoch. And so if you can check this condition very easily, and if it's not true, that's where the crisis is happening. The crises we looked at, there were application configuration errors, database configuration errors, request routing, and overloaded front ends and back ends. And all of these were easily detected, but the identification was the difficult task. Yeah.
So why is it common that you just specify these things over whole clusters? It seems like oftentimes you'd want to say that about some end user that to some level that the end user only sees a certain amount of latency, as opposed to the second bullet, which says that it's a property of the entire cluster.
I think you care about the properties of all the requests coming into the system, and you want to make sure that, say, the slowest requests in the system are not too slow, right? Or that the 99th percentile of latency of all the requests is not too high. So you look at all the users in your system and make sure that the slow ones are not too affected.
Do you also consider crisis prediction? You could imagine that 91% of servers have latency less than milliseconds and sort of running at edge. You can tell it's going to happen if you looked at it. Did you consider that kind of scenario?
So we considered using the fingerprints for predicting that a failure will happen, but it turned out that if you just make the SLO stricter, For example, you decrease the threshold from 100 milliseconds to 50 milliseconds. That also would give you an relatively accurate predictor. At least it was more accurate, or roughly as accurate as using the fingerprints themselves. So we tried that, and in this particular case, it wasn't really useful. Okay, so now how do we actually create these fingerprints? And the goal of the fingerprint is take the system state, the performance metrics being collected, and create this compact representation. All the performance metrics, we treat them as arbitrary time series. So we don't make any assumptions about what they represent, what they are, and very often there are these application-specific metrics that we had no idea what they really mean, right? There are some of the metrics we understood, like workloads and resource utilizations, but the majority of these metrics were specific to HS, and we didn't know what they are. You can think of the system state as, if you think of one server, that server is collecting 100 different metrics over time, so that's the state on that machine. But you have hundreds or thousands of these servers, and that's the system state. Now I have the definition of the crisis. I know that there are periods that are OK, and there are periods where the crisis was happening. So our goal is to take the data from the crisis and create this crisis fingerprint from that. And we do this in 4 steps. In the first step, we select the relevant metrics. Right? This is where we use the feature selection step, because it turned out that using all 100 metrics is just too much data, and we select just 20 or 30 metrics. In the second step, we summarize each of the selected relevant metrics across the whole cluster using quantiles, because we don't want to remember, say, 1,000 different values of a CPU utilization. In the third step, we map each of the metric quantiles that we computed here into 3 states. It's either hot, normal, or cold, depending whether it's the current value is too high or too low compared to some historic data. And finally, because each crisis could last for a different amount of time, we average over time to compute this single fingerprint. So in the next 4 slides, I'll talk about these 4 steps in detail. So first step was selecting the relevant metrics. The reason we did this is that we tried creating fingerprints using just all the 100 metrics, and we also tried creating fingerprints using the 3 operator-selected latency metrics. And none of these really provided us with high identification accuracy. With 100 metrics, it was just too much data, and the fingerprints were too noisy. With just the 3 latency metrics, there wasn't enough. We were not capturing enough information. So what we did is use a feature selection technique from machine learning called the logistic regression with L1 constraints to select the smaller subset of relevant metrics that are correlated with the occurrence of the crisis. The way you can think about it is that we're building a linear model where inputs are all the metrics being collected on the system, and the output is a binary, and we try to predict whether there's a crisis or not, and we try to use only a small subset of the metric, but still get an accurate model.
This logistic regression of 400 times 100 inputs, or just
this was
100 inputs?
This was 100 inputs, 100 features. One metric was one feature.
And so you're taking the average or something over the whole set data center, or over the whole cluster?
So the way we actually did this was that we, the crises, let's see if I go back. Well, so we had the SLO per machine, which were the latencies, the latency metrics and the thresholds, and this is what we used to create the 2 classes.
There were 400 separate labels per time step. Every 15 minutes there are 400.
Right. Yes. Yeah.
Like you would have a lot of structure both in individual features as time goes by, periodicity and so on, as well as you could have correlations between features where, say, some servers become overloaded and others have lower loads. Did you explicitly try to take into account the temporal structure as well as the cross-feature structure somehow?
So I'll get to the temporal structure later, but in terms of dependencies, no, we haven't tried to explicitly capture that, because all we did is select these metrics, and then so what you actually have is we have many instances of crises, and we run this per crisis. And so after for each crisis, we get maybe 10 or 20 metrics. but we have many instances of crises, so we actually take the most often selected metrics as the set of metrics that will be the input to the fingerprint.
Do you vote individual feature selections to do it in one single meta feature selection?
The way we did it this way is that we wanted to actually also identify which metrics are useful for each individual crisis, just so that we could tell the operators that here, for this crisis, these 5 metrics were the crucial ones, and so on. And the one thing that I'd like to point out is that some of the metrics we selected were these application metrics that the operators knew that they are collecting them, but they didn't really realize that they're actually important for crisis identification, right? And this highlights that there's just so much data that even the people who work with the system every day, they didn't realize that some of these metrics would help them. And so once we told them, look at these 2 metrics really help us, so you should start looking at them as well, they started using them. Right? And this is, again, we didn't really assume anything about meaning of these metrics, so that's what makes it powerful.
How often do you reevaluate this? You can easily imagine a situation where you see a new type of crisis show up, where the relevant metric was something that didn't matter before because you have been
Right. So what we do is every time a new crisis happens, after it's over, we run this feature selection on that new crisis, and we potentially add new metrics in, and we might remove some other metrics from the set. Yeah. All right, and so I'd like to point out that we're using this classification setting here only for the feature selection. We're not actually using these models later to create the fingerprints. Now, in the second step, we like to take all the selected metrics, all the relevant metrics, and summarize them across the whole cluster. The reason is that if you have a CPU utilization metric, for example, you have 400 measurements, and you don't want to remember all 400 values of this. So on the top, you see a histogram or distribution of observed values of this metric, and we characterize the distribution using 3 quantiles, the 25th percentile, the median, and the 95th percentile. We selected these ones by visually inspecting the data, but you could also automate this process once you have some labeled data and pick the quantiles that actually give you the best accuracy. And the advantage of this is that this representation is robust to outliers. Even if 1 or 2 servers report extremely high values of metrics, it doesn't affect these quantiles that we're computing. And it also scales to large clusters, both in terms of if we're adding more machines, we're still representing the fingerprint using just these 3 quantiles. And also there are techniques to efficiently compute quantiles given large input sizes.
In the previous step, when you select the features, when you train the logistic classifier, so for each crisis, you're assuming you get 400 examples of failing of crisis behavior for all of the servers. So you're assuming that for each crisis involves all of the servers?
So we take, when the crisis happens, we take some time around the crisis, say 12 hours before, 12 hours after. So it covers both the normal periods when the system was okay, and it covers also the problematic periods. And so the number of data inputs is 100 metrics, but then the number of data points is 400 times the duration of the crisis plus some buffer on both sides.
Right. You are assuming that all 400 servers are exhibiting some kind of crisis behavior.
If not, then they just fall into the normal class.
Right. So how do you label the crisis?
So for each crisis, in this particular case, each server is reporting the 3 latencies. And we know the thresholds on each latency that actually matter. They're specified by the operators. For each server and each point in time, we know whether that server is okay or not.
So in this work, the servers all were doing the same thing, unlike, say, the Amazon model where they get it.
Right. So this works kind of best for, say, a single application, for like application servers belonging to a single application. Right. Yes. So what we tried, and that wouldn't really work, is using, say, mean and variance of these metrics, because these are really sensitive to outliers, and a single server could significantly affect the values of these. And we also try using just the median of these values, but that didn't give, in some cases, they didn't give us enough information about the distribution of these values, and we had to add a few more quantiles.
Robust about that. So I think that outliers would be where the problems are. I mean, why?
Because we were interested in crises that affect a large fraction of the cluster. In this case, right, the crisis only was happening when at least 10% of the machines, in which case, at least 40 machines were affected. Right.
So you picked asymmetric
right.
quantiles, right? You picked 25 and 95. So is there an implicit assumption that you're more likely going to, because you're quantizing this way, is there an implicit assumption that that high is more likely to be bad?
In most of the, we did this by visually inspecting the data, and we noticed that a lot of the metrics, when something breaks, is usually the metrics go up, or they don't drop below 0, say, right? So we want it to be more sensitive on the high end. But again, this is something that you could automate, and once you have some labeled data, you can try different quantiles and pick the ones that actually work better.
If you had, say, rate metrics as opposed to latency metrics, then flow is probably more interesting.
Right.
Okay.
Also, these are numbers that you use for across all the metrics. It's not just an example for CPU.
Yes. Yeah.
Okay, so you used exactly the same.
Right. Yes. Okay. So now in third step, the goal is to take the observed raw values of the metric quantiles, like the median of CPU utilization, and map it into hot, normal, or cold values. So to say, kind of capture automatically whether the current value is too high or too low. So what you see on the 4 fingerprints on the right, we call them epoch fingerprints, because now for every single time epoch, we have one row in this rectangle that represents that particular time step. And the gray represents the normal value, the red represents too high, and blue represents too low. So what you see here is that there's about, here we use about 11 metrics, each one captured using 3 quantiles, so there's about 33 columns. And so we achieved 3 things here. First, we can differentiate among different crises. The crises, there's 2 instances of the same crisis on the top, and visually the fingerprints look very similar, while there are 2 different crises on the bottom, and the fingerprints are different. The second thing is that the representation is very compact. Right? Remember that we started with 400 machines, each one reporting 100 metrics over a period of time, and we can really compactly represent it here. And on top of that, it's intuitive, because you can quickly see that there was this one metric that first dropped at the beginning of the crisis and then got back normal, and then maybe the high quantile increased. And when we actually show these fingerprints to the operators, they were able to identify some of these problems just by looking at this heat map, right? So we thought that that's really cool that they can do that, and they could verify that whatever is captured here actually represents the problem they were looking at. What we tried is using the raw metric values. The problem there is that, say, some of these metrics could achieve really high values during the crisis. So comparing the vectors would really skew, or these extreme values would really skew the comparison. And we also try fitting the time series model here, because we noticed that there are these daily patterns often in workloads and CPU utilization. And we tried fitting the time series model, but for many other metrics, there were no significant patterns. So doing this discretization based on this model didn't really work very well.
You just had 3 kinds of crises, or 4?
We had about 10 types total, and had 19 instances total. Yeah. And finally, the last thing we have to deal with is that different crises have different durations, so you can't directly compare the rectangles you saw on the previous slide. And that's one thing that wouldn't work. The other thing that wouldn't work is just using the first epoch of the crisis, because often the crisis evolves over time, and you want to capture that information. So the simple thing we did is simply average over time. Take all the fingerprints during the crisis and create a single vector that represents that crisis, and we would compare different crisis fingerprints by computing the Euclidean distance. So these are the 4 steps of how we create the fingerprints. But now we also need to define the method of how we use the fingerprints to identify the problems in real time. Again, you see the timeline on the left. First, the crisis is detected by violation of an SLO. And then what's important here is that the operators of EHS told us that it's useful for them to get a correct label for a crisis during the first hour after the crisis was detected. The reason is that it often takes them more than an hour to figure out what's happening. And so during the first hour after the crisis was detected, we performed this identification step. What we do is we update the fingerprints first, given all the data that we have, and we compare the fingerprint to all the past crises we have in our trouble ticket database. And we either emit a label of a similar crisis that we find, or we could emit a label, a question mark that means that we haven't really seen this crisis before. So over time, what you get is these 5 labels that you first try to do the identification when the crisis is detected, and then every 15 minutes later during the first hour.
So your fingerprints are averaged over the whole crisis, right?
Or during the first hour of the crisis.
Okay, that makes sense. And are you comparing always versus the first hour average, or after 15 minutes to like a 15-minute average?
We would compare the first, say, 15 minutes or half an hour to the fingerprint of the whole hour for the past crises. And actually what turned out to be crucial also was to include the first 30 minutes before the crisis in the fingerprint. In this case, actually, here, the first 2 rows are the 2 15-minute intervals before the crisis was detected. And in this case, everything is normal. But in some of the other crises, you see that these metrics were high even before the crisis started. And so using those first 30 minutes and adding it to the fingerprint was crucial, or increase the accuracy. And once the crisis is over, we update the relevant metric, right? We run the feature selection step, and we update all the fingerprints to use the same set of metrics. And finally, the operators would add this crisis to the trouble ticket database with the right label.
Say the operator didn't notice the crisis, would your system be useful in detecting it? Or would you find similarities to normal?
So we didn't deal with the detection part. We took that definition of the crisis that they gave us, which was defined in terms of the latency metrics. And so we treated it that's input, and we didn't really look at whether we could do a better job. We tried using these fingerprints, but we couldn't really do a better job in terms of prediction.
I'm not necessarily talking about prediction in advance of the crisis happening, but
yeah, we assume that somebody detects it, right, or you detect it using the SLO violation, and then this is when we trigger the fingerprinting. Okay. Yeah.
I wonder whether some failures can be due to the bugs in the program, like say 2 components communicating with each other, and like they are not totally consistent.
So you mean that the problem would not really manifest as increased latency?
Right. I mean that the root cause can the root cause of some failures not be like the system is overloaded or so on, but it's because there's some problems in the code.
Right. If this translates into increased latency, right, then we would detect it by checking the SLO, and then you could start the fingerprinting process on top of it. So yes.
So if the program bug doesn't lead to performance crisis, then you are not dealing with it.
Then yeah, we were not dealing with that. Yes. Yeah.
Yes. There's no way they can tell they shipped you the wrong book, right? Until you write back in a month.
All right. So next, let's look at evaluation. As I mentioned, we use data from EHS, from about 400 machines, 100 metrics per machine, 15-minute epochs. And the operators told us that 1 hour into the crisis is still useful in terms of correct identification. We had these 3 latency metrics and the thresholds on each of them that were given to us by the operators. And if more than 10% of the servers with latency higher than the threshold during one of the epochs, that constituted a violation and the definition of a crisis. We had 10 crisis types and total 19 instances of a crisis. There was one crisis type where we had 9 instances, another one then where we had 2, and the other 8 where we had only 1 each. So it's like same instance, same crisis happens 10 times. Those were the 10 instances, occurrences of the crisis. And so, and these happened during a 4-month period. The main evaluation metric that we care about is the identification accuracy, right? How accurately can you label the problem? But before I get to that, we actually defined what we call identification stability, because every time a crisis happens, you actually emit five labels. You might start with saying you don't know what this crisis is, and then you start labeling it correctly. And we require that we stick to the first label. Once you assign a particular label of a crisis, you will not change your mind later, so that the operator is not confused. So here in the top, you see 2 instances of unstable identification, where we first change our mind from crisis A to crisis B, and in the second instance, we change our mind from crisis A to I don't know, right? So both of these would be unstable, and even if A is the right crisis, we wouldn't count them as correct. So in terms of crises that were previously seen, if we were identifying a crisis that was previously seen, the accuracy was about 77%. This means that in about 3/4 of the crises we can assign the right label, and we can do this on average after 10 minutes once the crisis is detected. So potentially you could save up to 50 minutes of the identification performed by the operators, which seems pretty good. And hypothesis is that we can't really verify that if we had shorter time epochs, we could probably do it even faster, but we had the 15-minute time intervals. For the crises that were previously unseen, the best we can do is say 5 times, I don't know what this crisis is, right? And that's the definition of accuracy here. And for 82% of these crises, we're able to do this correctly.
Is that statistically relevant, or is just the numbers of samples you have for each?
You mean why isn't it higher?
Why is the previously unseen accuracy higher than the previous?
Oh, I mean, these are almost completely independent problems, right? So there's no reason why that should be higher than this one.
Are the previously seen crises or training data effectively? The way you described it was that you update the vectors, the feature vectors of each crisis.
Right. So I mean, you could get, as you get more data, the accuracies actually do increase over time. Because the more data you have, the more samples of different crises you have, and you can tune your thresholds, identification thresholds better. So there's definitely that effect. Yeah.
These accuracies were computed causally, right? It's not like you did a whole one out. You sort of described, did your temporal thing, and then emitted accuracy, and then measured yourself and do it again.
So the way we did it is that because we only had this one sequence of 19, we actually we reshuffled them many times, I think like 40 times. So we created 40 new sequences, so we can test the identification in different order of these crises. But for each sequence, what we did is, we started with 1 or 2 crises, and then we went chronologically in that order.
This is averaged over 40?
Across 40.
Is this a net win for admins? Is about 30% of the time you're...
I think so. I mean, yes, you in 30% of the time, you still wouldn't give them an incorrect label, but they would still be checking what this crisis is anyway. So it should still give them and should still help them. And also in practice, the way we did this evaluation was we only consider the closest similar failure or a crisis in the past. But in practice, you might look at the top 3, for example, crises, right? And the operator might decide himself which one actually looks best.
So I'm curious about this reshuffling, though, because it seems like in these systems, oftentimes the systems change and get updated over time. And by reshuffling them, it seems like you're using future knowledge of what happened after the system's been updated to make predictions about crises which happened in the past. Did you find that if you didn't do this reshuffling, you just ran it on a...
Well, we definitely wanted to do some reshuffling because otherwise we would only have a sequence of 19 crises, and we could compute accuracy, but it would be really based on very few samples. So that's the reason why we did that. And the time period was relatively short. It was just 4 months. So I don't think the system would have changed that significantly.
Blank memory with each run, right? So
Right.
you're not doing, so you wasn't doing, right, the reshuffling, it started completely clean for each of the 40 runs. So
Yeah, but if there's any changes over time.
Right, but you know, the crisis
knowledge about
5
that.
might tell you something about the crisis that happened earlier, really, but you know, reshuffling happened later. But yeah, I don't think this would have been. Obviously, if you have a longer time period, like year or longer, you might want to even start forgetting some of the fingerprints because as crises are fixed, you want to maybe delete them from your database.
How do you predict the label given the fingerprint? How does it miss that?
So we.
You map it to label somehow.
So we assume that there is a database of all the past crises that are labeled, and all of them have fingerprints assigned to them. We just compute Euclidean distance, and that's the similarity measure.
Out of the 23% where you weren't accurate for previously seen, do you know what percentage were like you gave back a question mark versus you gave back a wrong solution to?
It's a good question, but we haven't quantified that. Yeah, I don't remember.
Do you think the distribution of sort of the couple of them being common and then the remainder just being one-offs will generalize to longer time periods and larger systems? And if that's the case, wouldn't it be more effective to give them some sort of lower level information other than just the label? Since most of the time, a lot of the time they would just say this is new. That's not as useful as telling them here's some more salient features that are helpful to go.
Right. Well, so in the data from Amazon, again, I don't have raw counts, but there's a lot of these failures that I think in that system we saw a lot more things happening. At least as I remember, people running around and responding to emails that they had a kind of this wiki page almost of things that break, and they kept track of them, right? And many of these things were recurring again and again. And I think it's more likely happen for crises that are not that significant, because if this is a problem that really takes down the website, they really make sure that it's not going to happen again, right? For the less severe problems, it's very likely that it will happen again.
Yeah, I have a question about your computation of the accuracy for previously unseen crises.
Mm-hmm.
So for what cases you deem as predicting correctly and what are not?
So I only, in this case, I would only say that it's accurate if we have five question marks. That's the only case when we actually say that it's accurate.
So by issuing a question mark, you mean?
I don't know what it is. There's no similar crisis in the past.
But the definition of the crisis should be 100% right, because every time the SLO is validated, it will be deemed as a crisis.
So the crisis is happening. It's just that the same type of crisis hasn't really happened before.
So this 82% means that for 82% of the cases, you didn't assign any definite label for this crisis.
Right.
Okay.
And this is the first time we saw the crisis, so this is the best we can do, right?
Then for the accuracy for previously seen crisis, can I say it's like 50% as the baseline? Because you have 10 of the same can. So if I always predict that's type A.
The baseline is more like 10%. If I have 10 crisis types, I can pick one of the 10.
No. I mean, because if we assume there are some prior knowledge saying type A is more likely to be based on previous data, say.
Right.
Yeah.
Right.
Then baseline will be 50%.
Right.
Okay.
Yeah. So I mean, it depends on what is the different distributions of these crises and how often they occur.
Models other than nearest neighbor, because a learned algorithm might do that.
You could, but we didn't get to experiment with that. Moises actually, after I left, he continued working on this and he developed the more advanced models, and so he has some results on that. But I think the accuracy wasn't higher. It was a more flexible model and didn't maybe need as much training data, and yeah.
If you didn't use this really harsh metric, but you said that it's like the majority of the labels match the true one, how much higher would the number be?
Again, we didn't. We wanted to make sure that like we were using the strictest criterion, so that
So when you say So you reshuffle the sequence of 19, and you start, trying to identify each one. Does it start to count? After the second example, or?
So yeah, that's a good point. I mean, that's another thing that we experimented with. In the worst case is, you start with, say, 2 crises, right? So that kind of gives you at least some idea, and you count the remaining 17 for accuracy. That gave us a little bit less, lower accuracy, maybe 70%. But when we started counting after 10, that's when we achieved this. So once you have enough training data, that you can adjust your thresholds correctly based on the data you've seen in the past. All right, next slide. So the closest related work is this paper from SOSP 05. It has some overlapping authors. Moises and Armando Fox were in that paper. What they designed there is they called failure signatures. The main differences were that each signature was for an individual server, nor for a whole large-scale application, so it doesn't directly apply to this scenario. And it was also, the process was also a lot more complex because they were creating these classification models per crisis, and they were maintaining a set of them. They were removing some of them, adding new, and they were actually using, classifying the current crisis according to all these models and using that to decide what is the label of the current problem. And we show that we're doing much better by using our fingerprints. So to summarize fingerprinting, I presented crisis fingerprints that compactly represent the state of the system. They scale to large clusters because we use of only a few quantiles to capture the metric distribution. And they also have intuitive visualization so that both we as the designers and the data center operators could understand what's really capturing these fingerprints. The feature selection technique for machine learning was crucial for selecting the right set of metrics here. And we achieved approximately identification accuracy of 80%, and on average after 10 minutes after the crisis was detected. In terms of impact with Microsoft, the metric selection part is now being used at one of the Azure teams to diagnose their storage systems. And we also submitted 2 patents, one on the metric selection and the other one on the overall fingerprinting process. There are no questions. I'll move on to the second part. I'll briefly go over workload modeling of workload spikes. So in this project, the goal was to create a generative model of a workload spike that we can use to synthesize new workloads and stress test web applications against these workloads. So spikes happen a lot, right? Like the one that happened after the death of Michael Jackson, where they saw on Wikipedia about 5% increase in aggregate workload volume, but 13% of all the requests coming to Wikipedia were directed to Jackson's article.
What percentage of requests were going to Michael Jackson's article beforehand?
It was one of the hottest pages, but still, out of the million Wikipedia pages, it was a small fraction, a lot less than 1%, say. So there was a significant increase in traffic here. So what we mean by spike, it's an event where you either see increase in aggregate workload to the website, or you have significant data hotspots, where there's a few set of objects that see this spike in workload. And we started working on this project because there was a little prior work on characterization of spikes. There's a lot of work on characterization of web server traffic or network traffic, but little on spikes and hotspots. And also there's a lot of workload generators that people use for stress testing, but very few of them actually let you specify spikes in the traffic that they generate, and they're not very flexible. So there are 2 contributions here. One is characterization of a few workload spikes, where we realize that these spikes vary significantly in many important characteristics. And then we propose a simple realistic spike model that can capture this wide variance of spike characteristics and that we can use to synthesize new workloads. So first, let's look at different workload characteristics that are important, or spike characteristics. For spikes in the workload volume, we looked at time to peak from start of the spike to the peak of the spike, the duration, the magnitude, and the maximum slope in the aggregate workload. And for data hotspots, we looked at the number of hotspots in this particular spike, the spatial locality, or whether the hotspots are on the same servers or not, and the entropy of the hotspot distribution, whether the hotspots are equally hot or there are some hotspots that are a lot hotter than others. So in the next two slides, I'll look at these four characteristics and show you that the spikes we looked at varied significantly in each of these characteristics. Now on this slide, you see the first two spikes. The one on the left is a start of a soccer match during the World Cup in 1988. In the second one, this is a trace from our departmental web server when 50 photos of one of the students got really popular. And on the graphs on the top, you see the relative workload volume coming to the website. And as expected, the workload volume increased significantly during the spike. Well, we also wanted to look at our data hotspots. So first, the object is in these traces is either a path to a file or Wikipedia article and so on. And a hotspot is an object with significant increase in traffic during the spike. So in these particular spikes, we identified about 150 hotspots for the first spike and about 50 hotspots for the second spike. And what I'm showing on the graphs on the bottom is the fraction of traffic going to a particular hotspot. And so that one page over there received about 3% of all the traffic during this particular spike. Now, there are these three other spikes we looked at. Again, from our departmental web server, when the Above the Clouds paper from RadLab got slashdotted, start of a campaign on ebates.com, and the Michael Jackson spike. And here's the first big difference. On the spike on the left, there is a significant increase in workload during the spike, but on the spikes on the right, the aggregate workload volume is almost flat. But these are still spikes because there are significant data hotspots here. During the eBates campaign, there was one page that was received about 17% of traffic, and the Michael Jackson, again, received about 13% of all the traffic. So there's the first characteristic. What is the magnitude of these spikes? The second characteristic that we looked at is the number of hotspots. On the left, again, you see 50 or 150 different hotspots. On the right, one or two only, right? So there's a big difference there. And finally, we wanted to answer the question whether all the hotspots are equally hot or some hotspots are a lot hotter. So on the spike on the left, these 50 photos were almost equally hot during the spike, while the Michael Jackson's page was significantly hotter than all the other hotspots in the system. Right? So these are the three characteristics that we looked at here, and the spikes vary significantly. The other question we wanted to answer is whether the hotspots are co-located on the same servers or not. Here we don't really know the locations of the objects from the workload traces because we only know which objects were being requested. So what we did is we sorted all the objects alphabetically and assigned them to 20 servers. And this is something that might not make sense for some storage systems, but we were interested in this in the context of the SCAD storage system that we are working in on Berkeley. And in that system, we're storing objects in this alphabetical order to enable efficient range queries on these objects. So what I'm showing here at the bottom are these 20 servers that have a bunch of objects allocated to them. And I'm showing how many hotspots were actually on each particular server. So what you see on the spikes on the left, there's a high spatial locality. On the very left, there's one server that has almost all the 50 popular photos. In the World Cup spike, there are 3 clusters of hotspots, whereas in the Michael Jackson spike, the hotspots were distributed across most of the servers.
Where did you get the Wikipedia traces from?
So they are actually publishing. There are 2 sources of data. There's Wikipedia publishes hourly snapshots of number of hits to every page. And there's also recently a new couple-month trace of individual requests of like a 10% sample that is available out there. But what we used were the hourly snapshots that they publish.
I don't quite understand the Michael Jackson one. Isn't that just a single document? So would you
right, but we found that there were about 60 other hotspots, which were, when we looked at them, these were the articles being linked from Jackson's page, which were not nearly as popular, but still pretty popular. So the point of this part was to characterize what the real spikes look like. We only looked at 5, but even in these 5, we found significant differences. So the conclusion is that there is no typical spike. If you want to stress test your system against these spikes, you can't just use one. You should really explore a larger space of these spikes. And that was the goal of the second part of this project, where we wanted to design a workload model to synthesize new spikes. You can think of this as there's this space of spikes defined by the 7 characteristics. So it's a 7-dimensional space, and we saw 5 examples of spikes in here. What we want to do is create a generative model that has a few parameters that control the characteristics of the spikes that you synthesize. I'd like to point out that we're not interested in inference, so I don't care about inferring which actual parameters would yield one particular spike. All I care about is that for any combination of the 7 characteristics, there exists some set of parameters that could give me those characteristics. So in the next slide, I'll tell you about how we design this generative model. So there's 2 components in this model, and there's 2 things that you need to synthesize a spike. The first one is the workload volume during the spike. That would determine how many requests a second you're generating. And the second part is the object popularity during the hotspot, which determines the probability of picking a particular object and generating a request against it. So to generate the workload volume with the spike, we simply take some workload trace that you might have from in your system, like the curve you see on the top left, and we multiply it by this piecewise linear curve. And so these are here are a few parameters that actually affect the characteristics like slope, duration, and magnitude of the spike. So this is the first part. The more interesting part is how do you generate object popularity and add hotspots to that popularity. So again, we start with object popularity without hotspots. These could be, for example, samples from a Zipf distribution, or you could use the actual object popularity from your system. In the next step, we select which objects are the hotspots. And once we have that, we adjust the popularity of these hotspots. So in the next 2 slides, I'll talk about these 2 parts of this model. So first, we wanted to pick which of the objects, all objects in the system, are hotspots. We wanted to have 2 parameters that control both the number of hotspots and the clustering of these hotspots. So we have this clustering process with 2 parameters, number of hotspots and L, which is the clustering parameter. And we perform the following. We start with the first hotspot and add it to the first cluster. And for all the remaining hotspots, we either put them in a new cluster with probability proportional to L, or to an existing cluster with probability proportional to the number of hotspots already in that cluster. After you're done with that, you have a set of hotspot clusters, and you assign these clusters randomly across your space of all the objects in your system. And this process is also known as the Chinese restaurant process. And so here on the right, you see a few samples from this process. For large values of L, we get almost uniform distributions of hotspots across your clusters, whereas as you decrease the value of L, you get more clustering and more hotspots are clustered on few servers. And so that was the goal, of have a few simple parameters that lets us control what the hotspots look like. And in the second part, we wanted to adjust the probability of these hotspots. We sample from the Dirichlet distribution, which is parameterized by a single parameter k. And again, the k determines the variance and thus the entropy of the popularity of these hotspots. So if you pick small k, you get probability distribution like the red curve over there, where you have a few hotspots that are very popular, which might match the Michael Jackson case. Or you have a large k, and you have hotspots that have very similar popularity, which might match the 50 popular photos at our department. Now, to summarize this part, we first performed spike characterization, where we looked at 5 different spikes and concluded that there's no typical spikes and they vary significantly. In the second part, we designed a workload generation tool that lets us flexibly adjust the spike parameters, and this is much better than all the workload generation tools out there that don't really let you add spikes to workloads. In terms of model validation, right now, here I'm showing you a comparison of a real workload and a synthesized workload. This is data from the 50 popular photo spike. On the top graphs, you see aggregate workload to the system, and in the bottom graphs, you see a workload to the most popular photo in the system, and they do look pretty similar. There's of course some dips over here that we could model, but that would make the model more complex that we wanted. So in the rest of the talk, I just wanted to go over some of the other projects I worked on and summarize. Yeah.
Yeah, I have a question about your piecewise linear function. How do you determine that piecewise linear function?
These are the parameters that you can pick yourself.
So it's like a trial and error process. You find those piecewise linear functions.
So the goal of this was not to start with this spike and create get parameters that would exactly match that spike. The way you would use it is that, I'm giving you a tool that has a few parameters, and you might stress test your system against. Maybe you start with spikes that don't have the slope, where the slope isn't too steep, right? And then you keep increasing that parameter, and you keep testing your system to check whether you can still handle it or not. That's the goal, right? So we don't want to infer the exact values of parameters for a particular spike, but instead give you the flexibility to tweak them.
So it's something like there will be some parameter like how many segments and what's the biggest slope for each piecewise linear. And then your model will automatically generate those synthesized data.
Right, yes.
Does the model allow us to assign the likelihoods of the existing data implicitly after with the whole construction? Because then if you just look at the perplexity of the data you already had and then just see if it's actually predicting the ones you have well or not. Or is that just not the route over? I mean, you seem like you had a more modular approach where you just had piecewise, but in the end, if you could just actually look at the likelihood?
You mean likelihood of
the existing spikes that you have?
You mean that in terms of trying to predict that they...
Basically, how likely that the model could have produced these spikes? How much did they agree with the model?
Right. I mean, so this is some kind of the ongoing work. Here, I'm just showing you for this one particular spike how closely we match that, but we're kind of still trying to figure out how do you really compare how realistic our spikes are compared to the ones we see, right? Because it's not trivial, right? Like, these curves look pretty similar, but how do you really compare them, right? Because of all the noise in there, you can't just directly compare the values, right? So we're still kind of working on that and how exactly would you compare it. Okay, so let me now quickly run over some other projects I worked on. The first one was on performance modeling, where we designed both the black box models of various systems, but also we are combining query execution plans with simple models of database operators to get flexible models that can extrapolate well to unseen workloads or unseen configurations of the system and could help the developers understand the impact of their designs on, in future workloads. The second project was on dynamic resource allocation, where we're using these performance models together with control theory techniques to do dynamic resource allocation for both stateless systems like app servers, and also for stateful systems like the SCAD storage system I mentioned a while ago, where you need to decide whether you're adding or removing machines, but you also have to figure out how you're going to partition or replicate the data onto the new machines. The other project was on detection of performance crises. As I mentioned, we're using anomaly detection techniques to notice changes in user behavior. And finally, for both this crisis detection project and the fingerprinting project, we designed intuitive visualization of the state of the system. Here we were showing the patterns of the user workload on the website where the operators could verify whether our anomaly detection technique is actually detecting anomalies or it's a false alarm. So the big picture was that all the projects I worked on were on applying machine learning to the monitoring data being collected in the data center and creating accurate models of workload, performance, and failures. And we're able to use various different techniques like classification, feature selection, regression, sampling, and anomaly detection. But on top of that, we're able to combine these techniques with non-machine learning techniques like visualization, control theory, or optimization to get even more powerful results. In terms of future work, there's just two projects I'd like to highlight. The holy grail of data center management is really doing automatic resource management simply based on performance SLOs for all these applications. Ideally, I just take all my applications running in a data center, describe how fast each one should be running, and the data center should automatically take care of assigning resources and efficiently provisioning all these applications. And here we really need to combine all the models of workload, resources, power together and use optimization techniques to get there. And the other project is on failure diagnosis. While I mentioned the crisis fingerprinting, that really only helps you when the crises are repeating. For some of the more significant crises that could take hours to diagnose, you really need to combine all these various models that we're building with traces of requests, dependencies, and configuration. Ideally, put all the information together to create a single tool, single intuitive tool that the operators could use. So to conclude, what I presented here is a case for using machine learning as a fundamental technology to automate data center operations. The main reason we need to use it is that these systems that we're building are too complex to understand. Fortunately, there's a lot of good sources of data in the data center that could shed in light onto the workload failures and performance of these systems. And it's just too much data to analyze manually, and that's why we need to use some machine learning and statistical methods to understand this data. Thank you, and this work is in collaboration with other grad students, postdocs, my advisors, and Moises Goldschmidt from Silicon Valley.
Question?